Okay, this is section 3, electric fields. Electric fields describe the space around a charge, even when there is nothing else for it to interact with. So if we have a charge in space that's a positive charge, it's going to have an effect on the space around it, just like the Earth would still have gravity if it wasn't interacting with the sun, or the sun would still have gravity if it weren't interacting with any of the planets. We have this because we know that the space around it is being affected. So what we do is we have a convention. The convention is that field, when we represent this with lines because it's not something that we can see. So we would have out of positive charges, radially out of positive charges. And this is decided because it's just a convention. So it was just somebody decided that this would be the direction. And that decision was made based on a positive point charge. So point charge is a tiny piece of positive charge. And we would say, okay, well, what would this Q do? What way would it force this positive test charge? And it goes ahead and it would push it. Oh, whoopsie. I just been to select it. It would push it away. Okay, now over here, and the negative Q, we would have, I'm going to change that to blue, we would have the field lines pointing in towards it, because if we were to put a positive test charge over here, what would happen is that the negative charge would attract it, so it would move towards it, and that's why the electric field lines go towards it. To get the magnitude of the electric field, we would either have K, absolute value of Q, I forgot the squared, over R squared, or E is equal to the force over Q. It really depends on the information you're given. So I would say it really is going to depend, but if we have, let's take a look at this. I'm actually going to take away the field lines. Oh, no, I don't want to delete that. And I were to take away the barrier here, what would happen is these two would exert an electric force on one another. So if I wanted to know what is the electric field of positive Q at this place instead of the force, what I could do is maybe I'm given the force between these two objects, and to figure out what the electric field would be at this point in space, and we're going to assume it's right there on top of that, we would just go ahead and take away, we would literally divide out. This is not working out for me, is it? Nope. We would divide out the negative Q. And it would just be, you wouldn't actually divide by negative Q. You would just divide by Q. All right. Now, two other major things. Oh, and the way you would go ahead and figure out the electric field is the same method that you would use for electric force. There would just be one less Q. So if you are trying to figure out how to do those types of things, I recommend watching the first video and getting your information from there. The other two things we needed to talk about are both an electric dipole and a uniform electric field. So an electric dipole is where we have field lines that go. We have two that are near each other, and we're just drawing the field lines for this. So it goes out of positives and into negatives. So right here, the field line would be, we would go ahead and have one here, and it wouldn't be perfect lines or anything, but we would end up having this. And then again, here, we would have field line going here. And out of here. Oh, that was really a terrible line, my bad. Okay. And if you draw just a couple more, I forget what it is. If you draw one more on each side, right, you end up with a spider. Okay. A uniform electric field states that everywhere between these plates, we'd assume that these are infinite plates that go up forever, and like a really large hallway. A student described that I really liked. So we have going to the right. So the uniform electric field means that the electric field is the same at any place in between these two plates. Okay.